IOE 413 Muscle Force Prediction Study Guide. Let us add one more muscle to the elbow model and analyze the optimum solution. The additional muscle has the opposite biomechanical function from the biceps brachioradialis and triceps muscles in the model. You can see the data in the table here. The important thing to notice is that the triceps muscle that we've added in has the opposite function. It's listed as having the function of extension here, while the other three have flexion. So what that means in terms of writing down the moment equilibrium condition is going to be that we will have the first part that will look similar from the previous problems, 4.6 x1 plus 3.4 x2 plus 7.5 x3, but since the triceps has the opposite function, it doesn't do elbow flexion, it does elbow extension, it has the opposite moment arm, so it's negative. So it's negative 2.0 times x sub 4, because the muscle force for the triceps here is x sub 4, okay? And that's equal to 780. So all we've done is taken the model that we had with 3 muscles and add one more, but the key thing here is the one that we added, x sub 4, has a negative moment arm, a negative coefficient in the constraint, because it has the function of extending the elbow as opposed to flexing the elbow. So part A of this problem wants us to formulate an optimization model having an objective function of minimizing total muscle force. Well, that's going to be pretty familiar to what we've been doing in the past, so we'll write min z is equal to, and we'll write out here is the sum from I is equal to 1 to 4 of x sub I, such that moment equilibrium is satisfied, but also that we have x sub I greater than or equal to 0 for all I equals 1 to 4. And that's our linear programming optimization problem for part A. Part B of this problem wants you to demonstrate that it's impossible for the triceps muscle to be active for this moment loading condition, i.e. there is no co-contraction of muscles on both sides of the joint. So let's begin by just assuming that there in fact is muscle force being generated on both sides of the joint. Okay, that the biceps x sub 1 and the triceps x sub 4 have optimum solutions that are positive. We're going to demonstrate that this leads to a contradiction. We're going to do it using complementary slackness. What we have here is c sub j times pi star a dot j times x star j is equal to 0. So when you apply complementary slackness here to x star sub 1 greater than 0, it implies that c sub 1 minus pi star a dot 1 has to be equal to 0. Let's plug in some values here for c and a. We get 1 minus pi star times 4.6 is equal to 0. We can solve that one easily. So we get pi star is equal to 1 over 4.6. Let's do the same thing over here. For x star sub 4 is greater than 0. We get c4 minus pi star a dot 4 is equal to 0. Let's plug in some numbers. 1 minus pi star times negative 2.0 is equal to 0. Easy to show that pi star is equal to -1/2. And here's the problem. Pi star equals -1/2 is inconsistent with pi star is equal to 1/4.6. That those two things cannot be simultaneously true. So we have a contradiction. Well, the same exact argument follows for x star sub 2 as being greater than 0 and x star sub 3 being greater than 0. The exact numbers are slightly different, but it's exactly the same argument. You could try it through it yourself and see. So you can go through each one of these conditions and show that, in fact, you end up with a contradiction if you assume that a flexor muscle is active at the optimal solution at the same time that the extensor muscle, the triceps, is as well. So that completes this problem.